A
I'm
guy did one 10 miles, and his laser was right on the lake.
Right.
A halfie.
Right.
So we're getting those, and we shouldn't be.
So when you say shouldn't, what I would ask is by what percent? So for example, yes, we're talking about the globe, and if you increase your height, blah, blah, blah. But you do know there's refraction.
Sure.
And so what I always challenge people is, so let's say we shouldn't see the laser for this laser test, but we do see the laser. So then I'm asking, so like, what's the error?
So what's causing that? Right.
Or what's the error? Like, we expected not to see the laser, we do see the laser. What kind of error are we talking about? It's always less than half a degree. So I don't know if you've ever done the math on that, but I do it on every single laser test.
With the formula of 8 inches times the mile squared, there is no degree.
Well, no, that's
if you're going to work with a degree formula, that's a different formula.
Right, that's the angular size formula. The one I was talking to you about, where it's size of the object, distance of the object, what of an angular size it is. So you could do the math either way. You could do 8 inches per mile squared to measure Earth curvature. You could use the Earth curvature calculators like GitHub, Metabunk, or you could even use angular size calculators where you need distance and you need height. But the error, and this is really important people understand this, wherever they say we shouldn't be able to see that but we see it, I say, but what's the error? The error is always less than half a degree, which means that out of you see 180 degrees of sight, if the error is that big, then that's not really a big error.
Okay, on 10 miles, we had 10 times 10 times 8
inches.
That's 800 divided by 12 comes out to 66.6. 66 feet is a 6.5-story building.
Right, but that's only if you're a halfie. So, but if you're standing 6 feet up, you need to use the Earth curvature calculator.
Calculation of error, is that more than a 6-story building for 6 feet?
Well, for starters, we have to make sure we're using the proper calculation. So the calculation you just used, 8 inches per mile squared, it's not an obstruction calculator. It's not to be used for what we can see. You have to use an obstruction calculator, which takes into account observer height. Okay, because you change the observer height, you change how far you can see.
So it's a different formula
so that's the first,
when somebody's standing up as to when they're laying down?
Yeah, it's not a different formula. It's a different input. So when they're laying down, you just subtract 6 feet from the observer height. But to answer your question, what's the error? You could run the numbers. 60 feet at 10 miles. You could figure that out. Like how many feet are in 10 miles? That's 52,800, right? So you have something 52,000 feet away, but it's 60 feet tall. That's quite small. But I mean, can't do the math in my head. But do you see what I'm getting at? It's actually a very small compared to the distance. So does that make sense?
I understand that it would appear smaller to your eye.
Right, but we're talking about the error, and I'm saying that I argue that the error is always less than half a degree, which means ultimately the error is very, very small.
So when we have these zoom cameras, and we're standing there and we're zooming in on this 10-mile away 6-story building.
Right.
And it brings it very close. We can count the stories. It doesn't look as small at all.
Well, no, I mean, the zoom camera is going to make it look big.
So why should we see it?
Well, because of atmospheric refraction.
Oh, so you think it's a superior mirage?
No, I'm not going to call it a mirage because
it's bendy air.
No,
it's bendy. What? Why? Why do we see it?
So you know that the air gets less dense. Like, you could go to the top of a building and you can actually
it gets less dense the higher you go.
You can actually feel the temperature change.
Yes.
So if you have a pressure gradient, they call it, or a density gradient. So like, air does have a density. It feels like it doesn't have density, but it does. So you have a density gradient. So the air here has a certain density. We go up even just 6 feet, 20 feet, 100 feet. The air is less dense. So if you extend this density gradient over many, many miles, light will bend a very tiny amount. It'll bend by a fraction of a degree, a tiny fraction of a degree. But it will bend. I mean, guaranteed. I mean, that's just the laws of physics. Light will bend in a density gradient. I'm not saying it'll bend a lot, but it will bend a tiny fraction of a degree.
Okay, I need to have a formula for that.
Oh yeah,
and then that has to meet testing of a number of circumstances.
Well, here's the thing, and you said this yourself about the difficulty of seeing a certain distance, you know, especially what time of year it is, because there's fog, there's humidity, there's different weather conditions. You can't come up with a formula that's going to say this is exactly how much light is going to bend, period.
Well, you can give a tolerance.
You can, right. So my tolerance that I always tell people is less than half a degree. It's like that's what I argue. Less than half a degree.
What would be the best and the worst tolerance for that 10-mile stretch?
Right. So the biggest number would be half a degree, and I think in my experience it's been like 1/100 of a degree, or less. You know, maybe the light is bending less than that.
So what is it over that 10-mile stretch?
I don't know. It depends on the seeing conditions. So are you familiar with the Skunk Bay footage? The Skunk Bay time lapse, I guess, was famous in Flat Earth circles a couple of years ago.
The red boat?
No.
What were they looking at?
There's a weather station, and I don't even know where Skunk Bay is. It's Puget Sound or somewhere. But there's a guy. It's like his hobby.
And he's
got a
looking
weather
at
station,
a building with many stories on it. He's
looking at it's like the bay, but there's a hill coming in here, there's a hill coming in here, and there's boats that go by. It's just a telephoto lens of a certain section of the bay, but the camera is bolted down and it's just recording, and then it's uploading to the internet. And then some people have made time lapses of Skunk Bay, the Skunk Bay footage.
Okay, so it's not a flat Earth or globe Earth thing. It's just
it's a weather guy.
All right.
And if you go to his website, it's all temperature, pressure, tides. You know, he's a weather guy. But this video, you can see the land bubbling up and down. You could see the water.
I've seen that.
You know, and it's and it looks like they're experiencing an earthquake. And so the question is, first off, the water's not moving. And the land is not moving. The land isn't physically getting bigger. So what's happening? Well, the light is bending. And if the camera's bolted down, and we can literally see these layers changing over time, what's happening? The light's being bent. Yeah. And I would argue the light's being bent by a small fraction of a degree. That's my argument, small fraction of a degree. I'm not arguing bendy light like you're seeing around corners or whatever. I'm saying a small fraction of a degree. And so when you take a look at these laser tests, I actually have a whole spreadsheet that I've dedicated to this. I haven't published it yet, but at some point I'm going to make a video saying, hey, next time you have a laser test or next time you have a test where you're seeing something that you quote unquote shouldn't be able to see, plug in the numbers and let's see what's the error.
I think I know what your video, the Skunk Bay, you're talking about. Did Mark Sargent do something about that?
I mean, lots of flat earthers have copied it, mirrored it.
Yes, where the water seems to hide the
the shoreline,
behind
right,
it there.
right, and then it comes down, and then the actual land itself starts to move.
So my question would be, why do we see it at all, ever?
Well,
I mean, despite there is refraction, I agree.
Right.
But at one point in the day, you see the land. At another point, when it's very hot,
right,
and the tide is in or whatever, then it's higher, and you can't see the land.
Right.
So I do understand that. But at some point, we see the land.
Yes.
Okay. And we shouldn't probably be able to see it. I don't know the distance right off my head.
So I would ask you to look very, very carefully into the word should. So like, what are the numbers you're running? And so a lot of times, and I saw this most accessibly like 3 years ago, it was all 8 inches per mile squared. Like every calculation done by the flat earth folks was 8 inches per mile squared. So they're like, we shouldn't be able to see this because of 8 inches per mile squared. And the thing is, that does not take into account observer height. So this guy at Skunk Bay, his camera is bolted to the top of his house, and his house is up on a little hillside. So his camera may be 50 feet above the water. So yes, he's going to see the land. He's going to see the land just about all the time.
Okay,
but
and again,
weird variations.
If that's what your objection is to that, seeing the land there, we have them where they're way down. and we can see the laser, and
Right.
and you're saying that there's refraction. Okay, but it's not going to be that much that
How
you
much?
can't see. This is what I want everyone to figure that out.
And I
what
figured
is
it
the
out.
tolerance?
Well, no, but not the tolerance.
Is it going
but
to be 67 feet?
you can't measure it in feet. We're talking about light bending. So when you say light is bending, you're not going to say light's bending 67 feet, because 67 feet is a lot on a football field. 67 feet is very little. in
Over 10 miles.
over 10
It's
miles.
exactly the example that we were just talking about. Over that distance, I think it's a lot.
We'll just run the numbers. 10 miles is 52,800 feet, right? 52,800 feet compared with 60 feet is not a whole lot.
Yes.
Thank you so much, man. Thanks for your hospitality. I appreciate that. But do you see what I'm saying? So and I just trying to do the math in my head. So it's 60 feet. Let's just divide by 10, right? So now we're back to 5,280 compared to 6, right? And then if you want to even divide further, I can't. I should pull up my
So why are you
calculator.
going why are you going from miles down to feet?
You want to compare apples to apples. So 10 is a small number compared to 60. So it's like, it's only 10 miles, but it's 60 feet. Well, 60 looks like it's the bigger number.
Well, 66 feet
Or
on
they'd
the
rather
curvature,
7.
and you going down to feet in the miles. It's feet and feet. So,
Right. So you're comparing apples to oranges. So let's say
Not really.
66 feet, and so this is 10 miles.
if I go miles per hour, that's still a legitimate.
Oh, sure. No, but there's nothing wrong with measuring it in miles. But what I'm trying to say is, what you're saying is 66 feet is a lot. I agree with you. 66 feet is the height of a
almost a seven-story
building. That's huge. But what's a 7-story building 10 miles away? Like, would you even be able to, would you even
And
be able
with
to
the zoom
notice
camera, I can see it
Right.
very close.
Right, but with your naked eye, a 6-story building 10 miles away is probably a dot that you can just barely see, right? It's a dot.
I don't know that.
Okay.
So I'm not going to commit.
So this is where, and I wasn't trying to put you on the spot.
But I can
so this
see
is where
Atlantic
5,200.
City from Wildwood.
Yeah. So, but I have to run the numbers. But if you do this apples to apples, so 52,800 feet, that's the distance. 66 feet, that's the height. Well, you can actually measure what this angle is. You can actually measure that angle.
Yes. So knowing the angle makes what difference?
Which means that is it the size of a dot? Is it the size of a peppercorn at arm's length?
That angle really means not really much.
Well,
it does not mean much, because either I can see it or I can't.
Right, but the point that I'm trying to make is that when you say 66 feet is a lot, it depends on whether you're standing next to 66 feet. If you're standing next to a 6-story building, 66 feet is a lot. If you're standing 10 miles away from 66 feet, 66 feet is very little. And so the point I'm trying to make is that if you measure this angle, or mathematically figure out that angle, and you find that angle to be less than half a degree, well, that's the error that I'm going to say for atmospheric refraction. I'm going to say less than half a degree.
Oh, so whatever we can see, you're going to say it's because of the refraction.
I'm going to say if it's less than half a degree.
And you're not going to commit to saying, well, here's a tolerance formula, and if we can find something that's not that, I'm going to still change my formula to meet whatever I find?
No, I'm saying I'm making a blanket statement that 100% of the observations will be less than half a degree off from what we quote-unquote should see on a mathematical globe. Because we don't live on a mathematical globe. We have an atmosphere. Atmosphere has density gradients. Light bends in a density gradient. That's the laws of physics. So if light bends in a density gradient, then I'm arguing that maybe over 10 miles, light might bend a fraction of a degree.
And what would a zoom camera do with that refraction?
The zoom camera won't do anything with the refraction. It just simply will make the target appear larger.
And what if we can see down to the bottom of that 6-story hotel?
Well, then that means that there is
with the zoom camera.
Right. Then that means there is a 66
but not with the naked
foot.
eye.
Yeah. So the zoom camera is
there
giving you.
refraction or not?
No, there's always refraction. We live on a planet with
so if I can't see the bottom floor of that 6-story building, you could say it's refraction with the naked eye.
Well, with the
but
naked
if
eye,
I zoom into it, then I see the bottom floor, then that's not refraction?
No. When I say you can't see it with the naked eye, you probably can't even see the building, anything bigger than a dot.
But I can see...
With your naked eye?
Yes.
So
I'm standing on the Ocean City boardwalk, and I'm looking at Avalon 20 miles away, and way to the left, you can see a little bit of wildwood sticking out beyond that.
But when we're talking about the building...
30 miles from
So are we
Ocean
talking about,
City.
you could see, like, are we talking about you're at night and you can see the lights?
Day,
okay, so it's
daytime.
Because
So I
can you
used
make
that
out,
as an example.
Can you like make out, like, you know, you could see the Sears Tower across Lake Michigan, and you could say, that's the Sears Tower. I know what it looks like. It's got a very distinctive shape.
Yeah, that's what this picture is up there.
Right.
Is
that's
Chicago across
Joshua Nowicki.
Yeah.
Right. Yeah, I have a whole thing on that.
Well, did you ever like go do real life experiences with that? I mean, I know you don't have a good camera, you said, but did you ever go? I mean, you said you saw the lights from the Cape.
I saw the lights
Wildwood
of Wildwood from Rehoboth Beach.
Rehoboth, okay.
Rehoboth Beach, Delaware.
So is that pretty much your real life experience?
Well, no. The thing is, I do lots of extensive measurements. I don't do field trips, so I do lots of extensive measurements where I live, like here in Norristown. So measuring the angle of the sun in the sky, and measuring the angular size of things. I built a little solar observer with like a pinhole camera thing.
Yeah.
So I've made extensive measurements. I don't go off on field trips.
Okay. Can I make a suggestion? Is that when you do this, you are basically saying this works on a globe. That's what you're saying.
With an atmosphere. It works on a globe with an atmosphere.
Okay. And what you're suggesting then is it can't work on a flat Earth.
Well, no, I'm not going to say that. These particular observations where we're saying if you can see a 10-story building and you zoom in with your P900 or whatever, you see it all the way down to the shoreline, I'm not saying that you can't do that on a flat Earth. Of course you'd be able to do that on a flat Earth. If the Earth were flat, you'd be able to see that building, okay? So the ability to see an object at a far distance, yes or no, can we see it, can we not see it? That doesn't necessarily say the Earth is flat or the Earth is not flat. Do you see what I'm saying? In other words, it's still open.
Okay.
So that's why that's why I do my very careful observations of the sun, moon, and stars, because those absolutely eliminate the flat Earth as a possibility. Like, for example, on the equinox.
Now I don't understand how you could say that.
All right, well, just pick the equinox sun. If you were to, like, even just take a GoPro or whatever, do a time lapse, and just aim it to like where the sun's going to cross the sky, and you have the sun is going to trace a line in the sky. Like, literally, it will be a ruler straight line in the sky for 12 hours. And meanwhile, the sun is supposed to be going from here all the way around to here. So it's a bit of a stretch for me. It's a bit of a stretch to say, well, it's perspective, it's atmospheric bending, it's this, to take a semicircle, like literally half a circle, and straighten it out into a ruler straight line, like by some magic. That's where I, have trouble.
Well,
and there's 100 more observations like that. Like the moon. We always see the front of the moon. We never see the back of the moon.
There are some people who think that the sun and the moon are projections.
Yeah, I've heard that.
And I don't know about that. And that's what I stay away from, really, because I'm telling people about the surface of the Earth. And I think there's a lot of errors that could be made when you observe the heavenly bodies.
Right.
So
there are errors that could be made, but then the question is, by how much? How many degrees are we talking about? Because the errors that I'm talking about in your long distance sighting, like these laser tests and seeing 30 miles, 20 miles, whatever, the error I'm talking about is less than half a degree.
Okay.
So when we talk about looking at the sky, what kind of errors are people saying that Glovers are making? How many degrees of error?
When you do the equinox and you get a straight line, that is what you can say. You can say, my test made a straight line, okay? But you cannot say, it proves that the Earth cannot be flat.
Well,
You cannot say that.
Okay, so all I'm saying is that if the Earth were flat, and I'm getting a straight line pattern of shadows, or even if you turn the camera, you see
Then
a
there's
straight line.
something else going on.
Then what that suggests is that, first off, that verifies the globe model. I mean, that agrees with the globe model. It doesn't necessarily prove the globe model. But like the globe model predicts a straight line of shadows on the equinox. We get a straight line of shadows on the equinox. So we haven't eliminated the globe. The globe is supported, but it's not proven. However, on the flat Earth, especially the AE map, if you're saying that the sun is traveling in a semicircle, like literally 180 degrees of a circle, and we see it as traveling in a perfectly straight line, there's, like it's really hard to reconcile those two. So, there's other versions of the flat Earth map. Like, are you about the Pac-Man model? Are you familiar with the Pac-Man model?
I don't teach any of that.
Okay.
No.
So the Pac-Man model, it's essentially the Mercator projection. So we have the equator, and then here's the North Pole is actually, like Antarctica, is the ice wall. So we have the ice wall at the south end, and then we have the North Pole, which is the ice wall at the north end. And then, so here's North America, and then here's South America. I'm drawing this upside down, so it's all horrible. But basically, so they say, well, the sun just travels. I'm sorry,
And then
the sun
it jumps,
rises.
it goes
the
underneath
sun,
and comes
the sun,
around?
Well, no. It disappears and then comes back, like Pac-Man. Like
I heard that, and
it's called the Pac-Man model.
I just don't know how that would work.
Well, but the way it does work is that if you're an observer, you see the sun traveling in a straight line, right?
Well,
so this
sure.
works perfectly on the equinox. If any observer will see the sun traveling on a straight line. Boom, boom, boom. But then it disappears here and it reappears here and it comes back.
Okay,
So it's another model. So when I say that seeing a straight line on the equinox disproves flat Earth, it really disproves the AE model, the AE map of the flat Earth, because it's a 180-degree circle, semicircle.
Yeah, there is something strange about it. I will grant you that, but I don't think there's enough data for that.
So,
and
so
if
collect
you're
more
doing
data.
observations, then I think you're going to be severely lacking in evidence as to really what the surface of the Earth is.
Okay, so fair enough.
I mean, you're going to say, well, you can reject that map, but what you can't say, I think you really need to do some field trips, because there has to be some data that you're not getting about the surface of the Earth itself.
Okay. So that's a very, very good question about like the surface of the Earth. And so like in the real world of like the world of engineering and building and construction, how do people measure the surface of the ground? And they use a theodolite.
Well, theodolites do not go very far.
Well, but if you were to propose the world's most expensive construction project, like let's say there's a $10 billion airport, right? A $10 billion airport.
GPS.
Well, the G in GPS stands for global.
Ground positioning system. Loran. Military had Loran.
But Loran was based on radar sites. So Loran, absolutely. But the precision that GPS gives us, it's measured in feet, But the point that I'm trying to make is, if you have this $10 billion airport that you're going to construct and it's 10 miles wide, what are all the guys are going to be using theodolites? Every single one of them is going to be using a theodolite. So when I hear a flat earther saying, "Well, theodolites are just so inaccurate," it's like, no,
I'm not saying they're inaccurate.
They're the most accurate instrument
they
out there.
Go that far
For measuring. Well, when you say go that far, like what do you?
Well, you
mean?
can't see that far in them. You can't.
It's got a telescope.
It's not as you don't see as far as a P1000.
Yeah, so you're not surveying for like 100 miles, So the zoom level, but I mean, a theodolite does have a telescope built in.
Yes, it does.
It's not the same level of magnification.
Right.
So yeah, if you had a P1000 and you had a theodolite, the P1000 would have greater magnification, but the P1000 cannot measure angles to a millionth of a degree, or not a millionth, but a thousandth of a degree.
And even with any tolerances, I don't think you need to be that nitpicky with it.
So, but the point that I'm trying to make is that if you want to measure the surface of the Earth, like I'm talking about the sun, moon, and stars. So let's say we have to throw out the sun, moon, and stars. We have to focus on the surface of the Earth. Well, how do you measure the surface of the Earth? With surveying equipment, like a theodolite. And then when you do it with a theodolite, when you measure the surface of the Earth with a theodolite, you find that the Earth curves at approximately 8 inches per mile squared.
But I don't think that you can use a theodolite to detect curvature.
So would you say that you could see a mile just fine with a theodolite? Like, you know, with the, it's got a telescope.
I personally have never looked through one.
Yeah, well, it would be an eye-opening experience. And there's also another thing called
I used a laser on the job. We had a laser that would only go maybe a quarter mile, not even that probably.
Yeah. Well, there's another thing called informally it's called a dumpy level. And it has either a 24x or a 32x telescope built in, but it has optics. It has leveling optics, so that, you know, if I hold it and I go up and down, that line is going to stay the same. So it's like if I'm holding it, I'm trying to hold it steady, but you know it's a handheld instrument. Then it's got a little line in there, so the line is absolutely level, right? You know what I'm talking about? If I put it on a tripod, even better. So when you look through that, you get a pretty good sense of like where the horizon is set. But the folks who have used a theodolite...
But when you use any kind of an instrument, you can move it up just a little bit and that will drop the horizon.
Not if it's a level. Of course,
I just
you could take a camera. Like you could take a camera.
If you tilt it up slightly, it will drop the horizon.
Right, but you're not looking through an instrument. You're looking through, say, a camera.
You just said a theodolite. So
a theodolite has a level
yes,
line.
but if you
tilt it up, that level line will drop. Well, for starters,
and the horizon will drop inside the telescope. You won't see it on the level line.
But the theodolite, it's a leveling instrument. Like it literally, the mechanics of it.
But there have been tricks done by some videographers who have tilted their camera up and said, "Look, the horizon's dropping." No, you tilted your camera up.
So, are you talking about where they took a look at the guy's video where he had the red fluid in a tube?
Yeah.
Okay. So if you have the red fluid in the tube
on the mountaintop, looking at
if you have the red fluid in the tube, is it fair to say that water is level in that tube?
Mm-hmm.
So if your camera, like running out of napkin space, so the guy's tube, it was like a rectangle of tubing. So it was a so let's say this was the red liquid, right? And I think the thing was like maybe only this big, 2 feet maybe. So you could tilt this frame all you want, but if water is level, and I would say the water is locally level, then this line is going to be level with this line. Like even tilting this frame, those two lines are going to stay level with each other, right? Well, now the guy's got a camera. And his camera was lined up with both of those lines. So it doesn't matter if he's like tilting the camera up. If he tilts his camera up, like let's say his camera is going to be photographing this. Like he's tilting his camera up, right? But if his camera is still level with those, then his camera is level with those. Even if his camera is aiming up slightly, if it's level with those two water lines, his camera is level. It's the camera height is level, even though the angle is up. So he's not saying the horizon is dropping because I'm tilting my camera up, therefore the horizon is dropping. He's saying the horizon is dropping from the level line. The horizon is dropping this way.
It was a camera trick.
But anybody can duplicate it. It wasn't a camera trick. The guy that did the critique of it, he was like, well, let me shift my camera. And so what he did is he put his camera here. And he said, let me shift my camera. Well, you couldn't see the other line. In other words, when he dropped his camera down, the guy who was criticizing the first video, he dropped his camera down and you couldn't see the first line, the water line. So in actuality, the guy who made the critique was doing the camera trick because he was like, "I'm going to tilt my camera." Well, then all of a sudden you couldn't see the water level. Do you remember that? Did you see that video? I forget what the guy's name was.
I'm not sure I remember the whole thing, but I know that there was a problem with the camera.
The trick was in the critique.
The camera is not the same thing as your eyes.
If you did your eye, you would be seeing the same thing. If you line
the
up the two
horizon always rises to your eye level.
The horizon, the eye is drawn to the horizon is the truism. And that's another thing. Remember how we started our conversation?
No, actually, when I take my 4-foot level and I hold it up to my iris and I held it level, I'm looking right at the horizon.
At the beach, sure, but not at the top of a mountain.
Yes, no matter how high you go, in an airplane, anywhere.
I would challenge you to duplicate that experiment at a significant height.
Well, have you ever seen any footage out of a cockpit of a airplane?
Oh, there's tons of footages, yeah, but very few of them, or
way
none
up
of them,
there.
are shooting
at 7 miles high, 37,000 feet. 37,000 feet.
Right.
It's up at your eye level.
It's like a degree or something below eye level at that height. Maybe it's 2 degrees.
Okay, so if you're saying it's a degree or 2 degrees down to ground, then it should be higher.
No, the planet is really huge. The planet
really
is really
huge. How huge is the equator?
25,000 miles around.
That's not that huge. It's only 8 United States.
So it's so huge that if you were flying 500 miles an hour, it would take you 2 days to fly around the entire Earth. Like literally, you're going 500 miles an hour, and you're going to be going for 2 days before you get around. That's huge. So, but if you run the numbers, like you say, the horizon at being at eye level, and I say, well, the horizon is a couple degrees below eye level. It's all, you can do the math. It's a simple geometry problem. And one of the things that's nice about the metabunk calculator, it has all the data. It has like the horizon drop value in degrees. It has the hidden value. It has the.
And I'm saying that we see past all tolerances.
Well, and I would ask you, measure it in degrees, and it's going to come back less than half. That's my challenge for you. Is like these laser tests. I can see the mirror. The guy's holding a mirror at the beach, and his wife is like going like this with the mirror. That one, where the guy is photographing and he sees this flash of light on the beach. So then run the numbers, and you'll find that it's less than half a degree. Every single time, it's less than half a degree. Which means we're not talking about a huge error. Meanwhile, the guy in South Africa, he's looking due east, and he sees the sun when the sun's right here.
No, when you go off like that, that's not due east.
No. Take the guy in South Africa.
Yeah, but
this
look, this is not due east from South Africa. That's not it.
That's due east from South Africa.
No.
Right there.
When you have a compass, all you know is where north is.
Okay, so
and
what's 90 degrees?
It changes.
What's 90 degrees from north?
It changes.
From somebody standing in South Africa. He's not moving. If he were in a boat, you'd be absolutely right. East is here, and he's driving in his boat, and east is here, and he's driving in his boat. East. Okay,
right.
That's as you go in your boat. But if he stays in South Africa, where's east for him? 90 degrees from the North Pole, right? It's 90 degrees from the North Pole.
I admitted there is something very strange about where the sun is rising, and that is left up. But I think that when you are honest about looking at great distances, you're going to see that we are seeing way too far.
Yeah, way too far if we didn't have an atmosphere. I agree with you there. Way too far if we didn't have an atmosphere. So like the laser test should fail. We shouldn't be able to see the guy at the beach. We shouldn't be able to see the mirror at the beach. They would all fail if we didn't have an atmosphere. If the Earth were just a mathematical globe, I agree with you 100%. We should not be able to see those distances. But if you add an atmosphere, which allows a little tiny bit of atmospheric refraction,
well, then it should be a tiny little bit of error, but that's not what we're finding. We're finding we can see the whole building.
Right, which is less than half a degree. It's less than half a degree.
No.
Do the math, and you'll find it's less than half a degree.
No.
Well, I mean, just like, for example, I don't have it off the top of my head, I don't have the formulas. I mean, I could derive it real quick.
Well, you can put it up on your channel, and I'll take a look at it.
Yeah, but like, for example, so here's the North Pole, and then the equator is approximately halfway. So this is all very rough. So the equator is representing where the sun is on the date of the equinox, and then so South Africa is, like say down here. So where this napkin is folded, that represents like approximately 180 degrees. So we'll say sunrise, sunset. So for this guy in South Africa, he's looking due east, he's looking due west, and he's looking due north to the North Pole, and then he's looking due south. So east is 90 degrees from the North Pole. So when the sun is here, this guy sees it in this direction. So like my question is, what's the error? Well, the error is about 60 degrees. So if the error is about 60 degrees for this guy, and I'm arguing that I'm allowing a less than half a degree error, it's like it's
on
a lot
the
different.
sun. We're back to the sunrise again.
Mm-hmm.
Why are we doing that again? Because that's your area of interest, and that's what you think is.
Well, no. All I'm saying is I'm putting it in perspective.
No, you're just going on the sun and the moon and the stars thing, and I'm thinking that you need to get down to earth and look at stuff that's on the ground and on the water and things like that.
When I do that, when I look at those things.
But you just admitted to me that you don't do field trips.
I don't do field trips.
Well, that's what you really need to do.
What I do is I look at the footage that's been filmed by flat earthers and I post it on YouTube. So when they post the footage, like, are you familiar with Ranty? He's over near London.
I've heard of Ranty. I'm not a people follower. Okay. I don't follow people. Okay. But I remember, like, the red boat. That was excellent footage. Okay. When it goes out of the bay, the big red boat, and it goes out. It's a liner and a shipper, and it goes out of the bay, and they follow it for more than a half an hour or whatever, and it shows how the refraction affects the boat, and it looks like it's upside down and all that stuff, and it disappears, but it's there because she zoomed in on it. So it disappears from your eye, but you can still see it.
Yeah, I understand that argument. But my point behind here is if I as a glober am arguing that an evidence that somebody says we should be able to see the laser at 10 miles or 20 miles, and I say, well, the error is less than half a degree. In fact, the error is almost always like 1/100th of a degree or 2/100ths of a degree. Meanwhile, we have this problem with the sunrise and sunset where what's the error? The error is 60 degrees. And it's like somebody can't say, well, my model is correct, even though I'm allowing a 60-degree error. And I'm saying my model is correct, I'm allowing a half a degree. Do you see what I'm saying? It's just
sure, when it comes to the things in the heavens, sure it does. But I'm talking about what's on the ground, what's on the earth.
That's why I say measure with theodolite. So what I was going to say is, I was asking you, if you thought a theodolite would be able to see a mile, because you said, well, I can't really see that far. Well, how about a mile? Well, there's a guy who photographed, he set up a marker, a surveying marker, and he was at a pond. It was literally a pond, a mile-wide pond, perfectly still water. He set up the marker, I don't know, 36 inches, say, above the water. I mean, like, with a measuring tape hitting the water surface. So he had this marker that was like a surveying target, like black and white. You could see it at a distance. Like those printer registration marks. The mark looks kind of like this, where it's like a checkerboard, where like this panel is black and this panel is black.
Okay.
And so, if you photograph that you could see that a mile away. You still see the little. Do you see what I'm saying?
Right.
So that was the center of that was exactly, say, 36 inches off the water, and then he was a mile away, and he put the lens of his theodolite exactly 36 inches above the water. And what you saw was that the center was about 8 inches down from level, from like the actual mechanical level. And then he reversed it. He then put the target where he was, and then he put the camera down. And even if you go the other way, it was still 8 inches down. And so the water looked perfectly flat, which is why I'd argue. The water looks
flat. There was
flat.
nothing at all to do with the water.
Well, no, but what I'm saying is that the water was actually 8 inches, had dropped 8 inches in 1 mile from level. So if you have a theodolite here, and it's shooting a level line, and then you have this target, the target was just 8 inches down after a
well,
mile.
I'm going to reject that because I don't really know anything about that.
Yeah.
Well, I can't be there holding their hand and making them be honest. So I can't know.
Okay.
There's a lot of information out there that's false. And it's tampered with.
Agreed. So that's why I always argue that people do it themselves. So on my channel, you won't find me saying a single word. I've got like 4.5 hours of original content. I never say what the shape of the Earth is. I never say the Earth is equal. I say get outside and measure it. You know, measure this stuff.
But you don't do it yourself.
Oh no, I do it myself.
But you don't go down to the shore and see Atlantic City from Wildwood.
Because then it requires driving to Atlantic City. So no, you can actually make a lot of measurements.
But you were down at the harbor or whatever you said.
Yeah, and I couldn't see it. I couldn't see Wildwood. I should have been if the Earth was flat. I should have absolutely been able to see Wildwood. So, but anyway, so you can learn a lot from looking up. You really can. A lot of people reject it. The thing about looking up is that it's free and it's in everybody's backyard. Like no matter where you live on Earth, everybody can look up for free. And there are certain things that when you look up are literally impossible on a flat Earth. Literally impossible. I mean, like the straight line path on the equinox. The only way that makes sense is if the Earth were
you're saying that, but I don't know that. I don't have that data, so I don't know that.
Yeah. Well, that's why I say, you know, try it yourself. Every one of my videos ends the same way. It's like don't take my word for it. You know, go and measure yourself.
So when NASA puts out something like that, what is your explanation for something like that?
Well,
and that's right off their website.
Sure. This is the Suomi NPP satellite, which is at a distance of about 120 miles. No, I'm sorry, it's a distance of like 400 some miles. So if you figure out, if you get a globe and you put a camera at a scale distance, that the same distance that the Suomi NPP satellite was, it looks like that. I mean, you need a fisheye lens. But then if you pull the camera back, I don't know where this photo came from.
But the proportions are not the same.
That's because you're closer. If you literally get
the outside diameter, the outside circumference, and all that of that circle must be proportionately.
So you could do this with this. If I pull out my camera, you can do this with this little globe. So this. Really horrible, but let's turn. So the United States is there, and so let's just bring. All right, where's the camera? So my hand is in the light. But anyway, if you see the United States, it's taking up a significant portion, right? You can't see any of South America, right? You can't see China. China is yellow. You can't see China, right? And if I just pull this thing back, you know, just pull it back, you can now see a little bit of China, you can see a little bit of South America. This is a very crude demonstration. You could do it with a GoPro. So I took a GoPro and I photographed my globe and I duplicated this picture.
When you pulled this back, the circumference was dramatically smaller.
Right, then zoom in.
It was proportionate.
Then zoom in. Then zoom in. So if here's the we'll call this the Earth, and I'm just going to put tick marks. And again, this is very, very crude.
So you're saying that they took a picture from out here and zoomed in?
Yeah, absolutely. Absolutely. If you zoom in on a sphere,
then it will look like
it
changes the circumference, the diameter. The proportions must be the same.
So the proportions must be the same, but a sphere isn't a circle. A sphere looks like a circle, but it isn't a circle, right? So if I put this right up against my eye, I still see a circle. But what circle am I seeing? I'm seeing the circle that's only this big around. Right? If my eyeball is right up against this,
right,
like I can only see, and let's number the tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. I just made this up. If my eyeball's here, I can only see from tick mark 3 all the way through tick mark 7. But what shape do I see? I see a perfect circle.
Right.
Like my eye is not going to see, like if you look at this really closely, it is never going to look like any other shape but a circle. So if my camera is here, like the Suomi NPP, very close to the Earth, that's why the United States looks like it's taking up, you know, half the Earth, right? But now you take the camera, and I'm actually going to take it all the way back here. Take the camera back here, and now draw our sight lines. And what you'll find is that the camera back here can see almost between 1 and 2, right? Between 1 and 2 and between 8 and 9. But the camera, and what is this camera going to see? It's also going to see a circle, but it has to zoom in. Of course, the thing is further away, so it's a small circle, but what if I zoom in? It's going to look like, you can make these two circles the same size, the same shape on your picture, but this I'm zooming into the Earth. Here I'm using a wide-angle lens. I've actually duplicated this with my GoPro. I literally took a GoPro and in my backyard, and it looks like this, and I literally moved the GoPro in, and it looks like this, and I just cropped them so that they look the same size, and I literally duplicated that on my in my backyard with a GoPro. So that's the explanation. Is the thing that a lot of times flat earthers don't realize is that there are captions. This photo has a caption, and if you follow that, it says this imagery was taken from the Suomi NPP satellite at an altitude of 540 miles. I'm just making that up. But like, you could literally find out that information. This photo also has a caption. This was captured by the XYZ camera on the XYZ whatever at a distance of XYZ. Like, all that data is out there. And if you run the numbers, it matches perfectly. It matches perfectly.
Or it could be CGI.
Of course it could be CGI, which is why I tell people to do this stuff themselves. You know? So I don't say the Earth is a globe because NASA says it's a globe. You know, like, that's a non-starter. Okay. But I can explain that imagery. That imagery makes perfect sense if you actually know the data behind it. So, you know, it was really a pleasure talking with you, and I appreciate you hosting and listening to me, and we had a good conversation.
Sure.
But